Okay, welcome everybody. We'll give people a couple more minutes to log in and then we'll get started. All right, let's go. So welcome everybody. Thank you for joining. It's great to see so many both familiar names in the attendee list as well as many new names. We've got a great speaker today and really excited to move forward with this. This is Bay Vision Virtual Meetup. For a couple of years, we were doing physical meetings here in the Bay Area in Cupertino. And, you know, it was in the evening or early evening. There was pizza and people would come in and socialize and drink beer and listen to a couple of lectures. We had 2-hour-long meetings sometimes. Seems like a different world these days. On the other hand, this virtual format it's nice to see we're really getting the opportunity to both widen our audience and also widen our range of speakers. So today, Professor Dan Stoyanov is joining us from London, I believe. Thank you very much for joining us. So before we get started, just a few words about us. For those of you who are not familiar, we're RSIP Vision, and we're in the business of creating computer vision and AI solutions specifically for medical imaging. From R&D to production, we do both novel research of technologies as well as very implicative implementation projects. We work across application domains and across modalities from cardiology, pulmonology, as well as more than one activity in surgical and video. These are some examples of typical projects that could be going on at any given time. And I can think of no one better really to enlighten our community about the field of surgical imaging and surgical video in general than Professor Dan Stoyanov, with a leg both in academia, leading one of the leading and biggest interdisciplinary centers for understanding surgical scenes, as well as being the chief scientist at digital surgery in industry. Dan is a thought leader in this field, and we are very happy to have him here. Yeah, so that's sort of what I had to say today. Dan will present his lecture, and then towards the end, we'll open it up for questions. You'll be able to type in your questions through the GoToWebinar platform, and then I'll read off as many of them as we get a chance to discuss and to answer. Yeah, so without further ado, Dan, I will transfer the presenter to you. Here we go. Take it away.
Thanks very much, Moshe. Thank you to you and to RSIP for this invitation. Can you guys see my screen now?
Yeah, I can see it. So looks to be all
good. Okay, perfect. Yeah, thank you once again for this invitation and this opportunity. You know, I'm sad to be missing out on the chance to be in the Bay Area in person and to share beers with you guys. At the same time, it's quite nice to be ending my day here in London and being able to present to a completely different audience. I'm going to spend the next half an hour talking about some of the work that we've been doing in surgical video analysis and understanding, and how that may lead to some potential clinical applications. The majority of my talk is work that we do at UCL, but I'll show some examples that we've done with digital surgery and also with Odin Vision. So most of us that work in the surgical technology space will know that video is now ubiquitously available in most operating theaters. So you see a few examples of surgical video images, ranging in application from neurosurgery to cataracts to laparoscopic and gynecological procedures. And the range is actually much larger, so cameras can be inserted into the joint cavities during arthroscopy to observe the surgical scene in there. And so this very, very rich signal from the operating site is the primary source of information that clinicians use in order to make surgical decisions, and it also contains a lot of information about the pathology, the activity, and potentially information about risk and other types of intelligence data that we may want to extract. It's currently, I would say, widely underutilized, so very rich signal, widely available, but the technology to be able to capitalize on it is still developing. But I think we're now at this point of the data being available, the technological capability being there, that we can start capitalizing on this and building clinical solutions. So I'll just show a couple of theaters to give context to the type of camera that may be used in surgery. So at the bottom left, you see a robotic surgical theater with the intuitive surgical system, and a variety of scopes may be used with systems like that to access different parts of the anatomy. On the top right, you see a surgical microscope, so a very different type of optical system, but again, capturing rich information from very narrow surgical field of view. And then there's a plethora of other devices. So I'm showing an example of a given imaging system that can be swallowed and travels through the gastrointestinal tract, capturing image information that can be used for diagnosis. So I hope you can all agree that the opportunity is there. So there's a very, very rich amount of information that we as computer vision scientists may be able to exploit and develop algorithms for. So I'll broadly split surgical scene understanding into techniques that are used to extract semantic information from the image. And this is really about understanding activity, or kind of building an intelligence report of the surgical site. I'll talk a little bit about the types of technology we'll be building to get a spatial understanding of the surgical site. And then also talk about the spatiotemporal domain, and in particular in time, we're looking at recognizing activity. And that could be used in process understanding, workflow improvement systems, or potentially in surgical training for understanding and classifying surgical skill without expert supervision. So I'll start with the spatial domain, and these are some examples of fairly early work now of using surgical video in order to map the surgical site. My apologies, I don't know why these videos are not playing, but I'll elaborate for you. So in both images, you're seeing video data from laparoscopic robotic surgery, and by mapping the motion of the camera and the 3D geometry of the surgical site, we can potentially use this information to provide augmented reality. So to fuse preoperative models on top of the surgical field of view, so that you can navigate better to the structures of interest. And potentially you can use vision information to also drive forces, so that you can deform some of these anatomical models that you want to overlay in order to inform the procedure. Another set of techniques that may be used during procedures is in endoscopy. So in endoscopy, we want to be able to map the entire gastrointestinal tract. And typically this is performed using a monocular endoscope. And unfortunately, with monocular vision, it's quite challenging to perform pose estimation and to link any measurements that you make in a time instant over time, so to map the entire environment. And this has been a very, very difficult area for computer vision historically. Now with deep learning, we are beginning to make nice progress in this space. So we can use the monocular image to infer depth maps. This is a really, really nicely posed problem for deep learning techniques because we don't need to handcraft model sort of shade from shading style techniques in order to do depth estimation. We can potentially train these systems on simulation. So once again, my video is not playing, but in essence, what you're seeing are depth maps that are estimated from simulation systems in the top right image, and how these models trained on simulation can be transferred to real endoscopic video in order to estimate depth from monocular endoscopy. Now we've recently embarked on a 4-year European project that is entirely focused on building computer vision systems, SLAM, structure from motion, for this type of application. So taking endoscopic images, which can sometimes be full of aberrations and artifacts within a deformable environment, and then mapping the entire gastrointestinal tract. So I'm just going to try to jump out and see why videos don't seem to be playing during my presentation. Okay, I'll restart and we'll roll with it as it is. And if I have to, I may just be trying to explain some of the work, but rather than being able to actually show it to you directly. So in this particular slide, we're looking at a very different type of spatial understanding, and it's an area that we've been building out for the application of vision in fetoscopy. So in fetoscopy, we're looking at inserting a very, very small camera and observing vessels on the placental wall, and the aim is to map out the entire vascular network on the surface of the placenta, and then use a laser to photocoagulate these vessels in order to sever blood flow between twins. The challenge is that the field of view of the fetoscope is extremely narrow, and so ideally we want to mosaic a map of the vessels on the placenta, and use this in order to ensure that all of the vessels have been photocoagulated with the laser. Unfortunately, conventional mosaicking techniques are just not robust in this case, and this is due to a number of reasons. There's a lot of artifacts within the amniotic fluid that make the image quality poor. The resolution of the fetoscope is also fairly low because these are still fiber-based systems, and the amount of paucity of features on the placental surface is also fairly low. And so using feature-based mosaicking techniques really doesn't work very well here at all. And so we've been working in this space for a number of years now, starting with looking at deep learning techniques in order to directly estimate homographies and estimate the mosaic from these buildup of homography transformations, and more recently looking at taking fetoscopic video and applying neural networks to segment vessels, and then to use vessel maps as the underlying registration metric that drives our mosaicking and transformation. So this is work that will be presented at MICI this year. Unfortunately, I really have no idea why the videos are not playing. They were working just fine a minute ago. So in essence, we're taking fetoscopic images, we're mosaicking them, we're segmenting them in order to predict vasculature, and then using this in order to perform the registration and find the mosaic. This tends to work much better than what we have seen so far with either deep learning based tomography techniques or with any of the pre-existing feature style techniques. So sorry, I took a pause there because I was trying to get at least some of these videos because they're really nice to play for you, but no such luck. Now it turns out most of my presentation, about 90% of it, is video based, so you may have to use your imagination and bear with me here. So if we move away from the spatial domain and we move into the semantic domain, the idea is really, can we take an image and try to understand what are the different image regions and what are they occupied by. And so they may be occupied by instruments or by organs or by other labels of semantic interest to us. And this is an area that has received significant attention, in particular around trying to understand the relationship of where instrumentation may be in respect to an organ. So this is some images showing examples from the ENDOVIS challenge at MICI in 2017. So this was data thankfully released by Intuitive Surgical, providing a fairly small semantic segmentation data set, but still a unique one and very important for our community, showing labels of instrumentation and also labels of some organs, in this particular instance, the kidney. And so with data like this, which is now beginning to emerge in our community, you can take semantic segmentation networks, for example, Deep Lab or one of the more recent models, and train them on this fairly small data set and show that this capability can be translated into surgical systems. A new data set that we're releasing together with Digital Surgery later this year, so this will be part of the ENDOVIS challenge in 2020, really goes a step beyond that. So it's 10 times bigger than the previous semantic segmentation data available for surgery. So this is just under about 5,000 frames, but it has extremely high quality semantic labels for cataract procedures. So we're building onto data that was released in conjunction with the cataracts challenge a few years ago, and we have we spent quite a lot of time over the past year and a half semantically segmenting these surgical videos with very high quality anatomical and instrument labels. And so very much hoping that some of you can join us and compete in the challenge to kind of move the semantic segmentation field forward in surgical applications. An area that we have devoted a lot of effort and time into is in semantic segmentation and tracking of instruments. This video won't play, but in essence, what we demonstrated in a paper published at ICRA in 2019 was that if we take a fairly small number of semantic labels of instrument junction points, so articulated robotic instruments, we can, and their connectivity. So you're labeling the articulation points on the tool and the connectivity of those articulation points. We can train systems that can, just from the image, estimate where the instrument is, where these articulation points are, and also the degrees of freedom of them. So it's a really nice result, but essentially fundamentally limited by the fact that it requires supervised labels. And so something that we'll be showing at MICI this year is how we start moving away from the need of having labels. This is particularly possible when we have robotic tools. So we've been using the DVRK in order to generate kinematic information of where robotic instruments may be in the surgical field of view. With the kinematic information, we can also produce synthetic masks and also synthetic renditions of where instruments may be. And what we're showing with this paper is really a first step towards moving away from systems that require huge amounts of labels, and using a combination of kinematics and simulation in order to train a double input FCN in order to perform binary segmentation of the instruments. I'm imagining, I might not even try, but imagining that the videos don't play again. These are just some examples of the data that we can present. So as you can see, when you compare this new approach on a fairly small sequence, we're getting a slightly better, for different data sets, it's a little bit more than this, but we're getting a better median IOU than some of the state-of-the-art models. But the real improvement that we noticed with this technique was that when we start corrupting the image data and introducing smoke, the models that we've trained are actually much more resilient. So this is the same video, but you have introduced synthetic smoke in it. And you can see the degradation in performance for all models that happens, but the improvement with the new network seems to be better. So I think that by using this sort of kinematic and simulation information in our training dataset, or to supersize the training dataset, we're beginning to get to building more resilient models for detection and segmentation of instruments. Now, of course, in addition to instruments, we may wish to segment information that is pathologically meaningful, and so there's been a lot of work around using AI and CNNs in gastroenterology, and in particular in order to detect polyps or potentially Barrett's neoplasia. In this work, we'll be presenting a paper at MICI again later this year, where we're essentially combining 2D feature extraction with a 3D segmentation head, which previously we hadn't noticed in this particular application space. So some of these models are now becoming so extremely resilient that they're being productionized. There's a spin-out company, Odin, at UCL, that is doing so, and of course there's a number of other activities in the same space. What we found is that the 3D segmentation head really improves the temporal coherence of the predictions. So if you're just using a spatial component, the prediction tends to jump around. With the temporal component, we're really kind of improving that temporal coherence, which is really important for the user experience when you're deploying this in a clinical trial or to your end users. We've also got activity in this space in upper GI procedures, and these are just some examples of how you might use models trained to predict attention zones. So in upper GI, delineating the healthy versus diseased tissue is much more challenging, and so maybe predicting the attention zones where the clinician needs to focus is a different approach to take to look at that problem. So in terms of semantic segmentation, we can look at delineating the image into a number of different structures, and those may be informing information about the instrumentation, but also around pathologically meaningful labels. So the final aspect of vision that I'm going to talk about is really around activity recognition, and this is taking the temporal domain of the video and trying to build systems that are able to recognize what is happening, and to turn this video information really into a report at the end of a surgical procedure, so that we can have some sort of a record or a report of activity, some analysis of the case. So we can look at this activity space or temporal domain space in a variety of granularities. So we can look at very fine events, such as, is the camera inside, is there bleeding, or very coarse events, such as phases. So I would say that the phase aspect of this domain is quite mature now, and this is some really nice work done in digital surgery to show how we can take the video and predict phases, and also the presence of instruments in two particular application areas. One is in cataracts on the cataract challenge data, and the other one is in endoscopic transsphenoidal surgery. So these systems are now very, very robust, and digital surgery is productizing them. And it means that you can take the surgical video signal that's essentially present in all procedures that contain a camera and turn it into a intelligence report of the procedure. So you can look at video libraries of an individual surgeon's performance, or maybe a team or a hospital, and start extracting metrics around activity and phases, and looking at variability and how that may be affected as new technology is introduced, or new AI systems or navigation capabilities come into the theater. So it starts to beginning to provide us an insight into activity, and hopefully also link that back to what is actually happening in the theater. So create systems that may improve workflow. I should say that these temporal labels don't need to be around phases. So this was some work that we presented at IPCAI this year, again in fetoscopy, where the temporal labels are really labels that are useful for us from a understanding and potentially from a navigation perspective. So here we're really looking at the video in terms of 4 labels, and looking at when the fetoscopic view is clear, which means that you may be free to fire a laser. When there's occlusion, and typically that would mean that one of the fetuses is in the field of view, or when there's an instrument and when ablation is happening. So building this sort of understanding means that you can connect to intelligent instrumentation, and you can prevent risk, because you wouldn't want to fire a laser when one of the patients, when a fetus is in the field of view. So we've seen that we can construct these sort of coarse systems very, very robustly, but it's of great interest to go into the more fine-grained detail understanding, and this is particularly so with a connection to surgical education and building AI systems that may evaluate or steer surgical trainees with respect to some analysis of their activity. So this is work really that has been pioneered at Johns Hopkins. We presented a paper on it at ICRA this year. It's essentially taking the SURGENE portion of activity. So this is a SURGENE is something that composes an activity, and activities is something that compose phases. Phases compose an entire procedure. So that's where we stand in the hierarchy. And if we look at the SURGENE for suturing, this can be a very structured workflow of what suturing using robotic instrumentation looks like. So you can see this structured workflow diagram. And when we're using a surgical robot, so this is data coming from Johns Hopkins on the Jigsaw's data set. It's essentially using a Da Vinci system, and you're getting robot kinematics as well as the video signal on a standardized phantom suturing environment. And we're trying to build a model that can predict the activity, so the fine-grained activity label, in addition to how far we have progressed during the particular action. And what we noted is that actually doing progress and activity recognition at the same time makes the system much more reliable. And of course, you can look at different ways of combining the video and the kinematic labels as well, in order to once again increase robustness even further. So I said that mainly surgical scene understanding can be split within the within these domains or these axes of a much larger domain, so the semantic, the spatial, and the temporal. But in fact, of course, there's a lot more information that we can gather from imaging during surgery. So unfortunately, with this particular video, it's going to be very, very difficult to explain this to you without the video working. But something that we've been working on for a number of years, and again, it will be presented later this year, is how we can try to discover motion artifacts within the video that may be not possible for the surgeon to see, but may embed information that's very important because it provides a cue as to where important structures are in the surgical scene. So this is work that originated at MIT, Eulerian motion magnification, and we've been trying to translate it into the surgical space. And with this latest effort, what we're showing is that we can design the filter, we can design this amplification filter in a very specific way in order to suppress the additional artifacts that may come from instrumentation or from other aspects of the surgical site which we're not interested in amplifying. Now, this is really, really important because actually, if you amplify the raw video, it becomes very, very difficult to discern which is the important part that the surgeon should be taking note of and identifying when a particular structure of interest may be. So with technology like this, we may be exploring a very, very different domain for what the computer vision can do in terms of identifying critical structures, in particular blood vessels, that generate motion that we might not be able to see, but that we may be able to amplify in order to identify where the vessel is. The problem is really to address further what happens when the camera moves or is unstable, because that creates additional residue. So with this paper, we can suppress the instrument artifacts, but there's still more work to do in terms of suppressing camera artifacts. Now, of course, another area that I think has fantastic promise is looking at the spectral signature of the data that we can harvest during surgery. So in addition to getting white light and RGB images, there's a range of technologies emerging or already established looking at spectral signatures. This could be multispectral or hyperspectral imaging, or imaging that relies on an imaging agent being inserted. And this type of technique can give us very, very rich information about not only the structure, but potentially the function of the tissue that we're looking at. The problem is that it typically relies on making some simplifying assumptions about the way that light or other energy signals, how they travel and interact with tissue. So it's a very, very inverse and ill-posed inverse problem. And here, using AI type techniques, we may be able to build very robust priors or potentially robust models that can alleviate some of that simplification process, which we have done in a much more handcrafted way previously. So I think this is a really, really exciting space, and it's explored by a number of top research groups around the world. Another area that I think is very exciting for vision in the OR is if we look at the wider room environment rather than just the surgical camera. So these are some examples of both academic and industrial work looking at how you may be able to estimate the pose of people, estimate where people are, estimate activity. And of course, when we're looking at intelligence reports of surgery, this is really, really important because the surgical camera tells you what the surgeon is doing at the specific surgical site of interest. But of course, the wider activity within the OR is also crucial to the type of outcome that you may achieve. So looking at the wider context and looking at team analytics, team communication, team behavior, team workflows, team best practice is another really, really exciting area. And there's a lot of opportunity of linking the surgeon's activity at the surgical site with systems that may improve the team activity within the wider operating room. So I think I will conclude here. My sincere apologies for none of the videos within my very video heavy presentation working. Despite being in an era of AI, it seems like a technological flaw still hamper us. So my sincere apologies about that. But I'm very happy to take some questions and to discuss any of the things that weren't clear due to the lack of video information in the talk and the presentation. So thank you, and my apologies once again.
Thank you so much, Dan, and thank you for soldiering on and filling in the gaps with your words, despite the fact that the videos we're not playing. It's always a challenge to put things into words instead of pictures. One of the themes you touched on that I found very interesting, and we've been finding ourselves doing a lot more of that lately as well, is the theme of using simulated or artificial data to supplement or even in place of real data. So obviously for tool segmentation and tool detection applications, that's even kind of a no-brainer because it's fairly maybe straightforward to create this simulated data. You mentioned the GI depth map estimation application, even for things like pose estimation or estimating head pose. We've been finding that that's very helpful. We've been doing it in other modalities like training on DRR and then running the algorithm on X-ray in the real world. So curious how you've been finding this in your experience. For the GI depth map application, it sounds like there you may not have had any real data at all. It might be building entirely off of simulation, right? For that depth map, unless you've been putting in a depth camera and then just supplementing that. So curious how you guys have been bridging the gap. Have you been using like GANs and style transfer? How ready for prime time have you been finding this kind of technology? Because a lot of these problems, right, in principle, they're solvable or solve problems if there's enough data, but that if is a really big if. And I think, right, across applications, this use of simulated data has been really picking up. Yeah.
Thanks. I think it's a great point. I think for some things it makes perfect sense, right? So for instruments, I think it makes sense. It also makes sense, right, to use the robot kinematics and to use that as your training data, because then you don't need to simulate so much, perhaps. For the endoscopic depth mapping, indeed, we have been using GANs and style transfer. We haven't used a depth camera, although we were involved in a project a few years ago led by Scuola Sant'Anna in Italy, who created a stereoscopic endoscopic camera. And so we are still hoping to be able to explore how we might be able to fuse some of the stereo information with stuff that's purely trained on simulation. So what we found is that you can potentially get this 2.5D or this depth map. How well it's calibrated is very difficult to evaluate, because evaluating your model is still a major challenge in our application domain. But what we found, curiously, to not work so well is if we want to then use these depth maps in order to estimate pose, that hasn't worked very well for us, or at least we haven't cracked it just yet. So we can do the depth estimation. You know, we get something that looks like it's a legitimate estimate of what the depth may be. At least qualitatively, it looks okay.
Mm-hmm.
But then, we thought that from there, once you've got the depth, then fusing these depth maps in order to make them kind of longer and to do the pose estimation would be, we would be able to progress with that much more rapidly than what we've actually found. So I think there's still a lot to do, and there's a lot to do in terms of validating. So validating whether, because you can make it work and it looks qualitatively good, and we can make a video out of it, what the actual metric space of the information you're calculating is. I think we still haven't really done enough in that space. We're trying to, but it's pretty difficult setting up some of these experiments. So Intuitive did a really nice contribution in terms of data last year at ENDOVIS 2019, where they had a laparoscope with a depth camera, and they're going to release this data. So you've got 3D and laparoscopic stereo views in animal experiments. And so that's probably going to be a very nice kind of ground truth data set for the community to use. But even in that experiments, they were finding that the quality of the data still suffers because parameters vary as you're taking the experiments. Things are not quite as fixed as you would have hoped that they would be. So I think it's a really exciting space how we go from simulation to real. But we need better evaluation data sets, and then for certain areas, like for example, detecting stuff that is pathologically meaningful. I think there, obviously, there's also the question mark of how do you make sure that you're not making up information, or you're not heavily biased towards what you've observed. So I think there's still quite a few open questions for us.
Yeah, all right. There's a bunch of questions coming in here. So let me try to pick one out here. Okay, yeah, this is a good question that comes up quite often from Kumara. How are you addressing the latency and real-time issues? Computer vision in surgical environments requires the algorithms run in real time with extremely low latency, right? So yeah, on the one hand, there's GPUs and they're always getting better, and a lot of this is just running off the GPU. On the other hand, I do think it's a good question.
Yeah, it is a good question, and I think I don't think that there's an answer that covers the entire domain. So I think it really depends on your application. So with some things, we found actually the fact that everything has gone towards these big models that you can load in the GPU is made some things much faster. So if you wanted to do computational stereo on HD or on 4K images, a few years ago, and you're kind of doing it with calculating, your disparity volume and then optimizing over it, you were hitting computational bottlenecks. Now, the training time is long, but once you've trained a model, it can execute in milliseconds, and so it's super fast. Now, if you're looking to run some of the heavier models, and you're looking at the temporal domain and so on, as the images become higher in resolution, and then you're facing different challenges of throughput. So I think it really depends on the application. You can always put in a bigger GPU, but it won't solve everything because you may still need to move the data around. And it really depends on what you want to do with the information you're extracting. So if you want to link it to robot control, I think you're in a really tough space, and probably you need to have predictive models that are kind of compensating for the fact that you're never going, you're always going to be working behind time, behind what was observed. So I think that's one way to do it. There's obviously a lot of work in model optimization and carving out parts of your model that you don't need to execute, and looking at really nice tricks to optimize the model. So that's another way of approaching it as well. So we're definitely not linking to robot control yet, but I think once we start doing that, latency will be a major bottleneck.
Yeah, that's a really good point about trying to compensate algorithmically for that latency by the predictive model. Yeah. Okay, I think we got time for maybe one more question. This is also an interesting one. Do you think spectral or hyperspectral imaging offer any opportunities for improving tool segmentation, or is this more for tissue evaluation?
I would definitely go more for the tissue side. So I think the whole idea behind using hyperspectral is that you're going to get information from the light penetrating different layers of the tissue, and that those layers may contain different absorption and scattering coefficients. I think with the tools being made from fairly homogeneous materials, I'm not sure you're getting that much data in that space. Of course, you could easily use one particular wavelength of a light and have something in the tool that is very sensitive to that, and then have a camera channel that just basically is used to solve your tool segmentation problem. So I think in a way, having a spectral fiducial, I think that is definitely one way of engineering a solution that solves the problem, that wouldn't require so much AI or algorithmic or data work, completely agree with that.
Yeah. Be solving it in hardware, basically.
Yeah, exactly. Yeah, and I think that may be if you have a great killer application, and that's the thing that you need to do, then I think that's a very 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 rapid way of doing it. You can probably productize it much quicker.
Yeah. We're not married to doing everything with AI if there are simple ways, but it has to be the business case for putting that in, right? Yeah. Okay.
Right. I think in academia, we still do some things in AI because we don't have access to the hardware, or because we don't have the capacity to engineer it, and we'll never be able to put it in human. But obviously, it depends where you're tackling the problem from.
Okay. Thank you very much. Lots of comments here. Great talk. Thank you. Lots of appreciation coming in from the audience as well. Yeah, okay. Thank you very much, Dan, and thanks to the audience for tuning in. I think you're seeing various ways to contact either of us, and we're looking forward to seeing you virtually and hopefully eventually physically again sometime in the future. So have a great evening, Dan, and have a great rest of your day, everybody else, wherever you may be. And we'll be in touch.
Thank you very much.
Thanks
you
very
a lot,
much.
and have a great day and a great evening, everyone. Thank you.
Bye.
Bye.